And yes, it's wonderful to have Rob Rutherford with us today. So Rob is the Managing Director of Red Metal Limited with over 30 years of experience in copper, gold and base metal exploration. And it is going to be awesome hearing from him today about the Sybella REO Discovery. It is not every day we get to hear a talk about a whole new deposit type. So strap yourselves in. This is going to be a great session. Please keep using the chat and we'll open up the floor at the end. And yes, thanks so much, Rob, for joining. It's amazing having you.
Thank you, Jess. Okay, so there we go. Forward-looking statements. So basically, we've basically made this rare earth discovery just out the back of Mount Isa. We've done some proof of concept drilling, some preliminary metallurgical work, and we've outlined what is potentially a new sort of weak acid soluble rare earth deposit type hosted in a granite. And the sort of project offers scope for bulk mining and simple metallurgical processing. So the results to date show we've got these weak acid soluble rare earth minerals in a favourable sort of rare earth minerals in what is a low acid consuming granite host rock. It's just 20 kilometres from Mount Isa. The bulk of the rare earths occur as soluble fluorocarbonate minerals, and we'll talk about that. The proof of concept drilling to date's identified these two rare earth zones within the granite, with each are about 1 kilometre wide. The rare earth mineralisation is open for about 14 kilometres along strike, and it's open at depth, and so it offers really vast tonnage potential. We've got some localised high-grade zones which we don't know that much about at this stage. And the proof of concept leach work has shown that we can get about 80 to 90% of the rare earths out quite quickly and quite simply. But there's a lot more of that work that's needed to be done. Unlike a lot of the rare earth projects out there, these minerals are low, and the granite host rocks are low in uranium and thorium, so they're environmentally quite an appealing target as well. So and the infrastructure is pretty exceptional. So I'll run you through a little bit that in a little bit more detail and show you some what we think we've found. So we got onto this thing about probably about 2010. I started looking at rare earths when the neodymium price went to about I think it was $180, $200 a kilo for neodymium there when China put restrictions on exporting rare earths. I had a look at the monazite types, carbonatite systems, and Western Australia, where you couldn't mine uranium in WA or thorium in those days. So I really didn't take much of an interest in the carbonatite thorium deposits. But this granite, what we ended up looking for was seeing if there was any ionic clay deposits in Australia. And in our own backyard, where we do a lot of copper and base metals exploration, we discovered a granite from the historic, Australia-wide granite databases. We looked up where all the most favourable neodymium-enriched granites were, and this one stood out. And it came out of the shot holes from a seismic traverse that was done by Geoscience Australia in 1994. And you can see this is the traverse here. This particular pluton or a phase within this Sybella granite, which is about 20 kilometres from Mount Isa. It had exceptionally elevated neodymium and praseodymium, and it was that realised that this is a section through there that's about 3 kilometres, but it's only these shot holes are only about 10 to 20 metres deep. But it showed us that there's elevated rare earths, neodymium and praseodymium in these rocks, which at the time was worth quite a lot, up to $180, $200 a kilo. So we took a bit of an interest. We went out there and had a look at it. It wasn't a weathering profile sitting on top of these granites. It was really just fresh granite to weathered granite, weakly oxidised granite on surface, but not the deep clay weathering like you see in Western Australia and some of the Brazilian stuff. So it was a little bit different. We then grabbed some fresh samples of this stuff and had a look at the rare earth mineralogy, and I'll show you some of that shortly. But a couple of the keys is that there's Mount Isa up on this top corner here, and we're only about just out at 20 km southwest of town. When we went in recently, we about a year or so ago, did all the heritage and landowner stuff, and recently last quarter did a traverse, really to try and repeat, but the drilling that was done by Geoscience in their shot holes, drilled a traverse along that and we call it the boundary fence traverse, and that's the boundary station boundaries. But what we found when we drilled it, each of these holes goes down to 120 metres depth. And what we found is that there's over a kilometre of width of a high neodymium on the eastern side, and another zone on the western side as well, which is also about a kilometre in width. And this goes greater than 300 parts neodymium and praseodymium, but basically it's about a third of a kilo of neodymium per tonne. It's open along strike to the north and south. We haven't drilled it out yet, but we think the strike potential is in our ground alone is about 10 kilometres. And there are these localised high-grade breccia zones. We drilled another 4 holes to the north on some more accessible track there, and we found, again, similar wide zones of this mineralisation, so on what we call the Donkey Dam traverse. So to give you an idea, this is the 2 traverses, the southern one and the northern one, and it shows really these big wide zones. I guess a thing to look at on this, you've got what we call the fresh granite boundary here. It sits around anywhere from sort of 10 to 30 metres down, and then above that you have this broken granite. And that broken or weakly oxidised granite has the same, there's no supergene enrichment, there's no change in the chemistry across that boundary. It looks pretty simple, but it's quite broken, and it'll probably be amenable to a different bond work index when it comes to potentially mining this thing. What we did find though in locally in small hydrothermal secondary overprinting sort of hydrothermal systems, we ended up with these quartz, these breccias, which have some quartz and iron oxides, and they tend to be even enriching the rare earths in the granite as a sort of a secondary hydrothermal enrichment, but they were only localised in scale. So to us, the real opportunity is this bulk tonnage potential. So as I said before, the granite is very low in thorium. That's maximum of 50 ppm thorium in the granite, but really it's quite low. It's only 20 to 30 ppm thorium, and quite very low uranium, only sort of 0 to 10 ppm, which is pretty background levels for a granite. So this is the sort of assays that we've been getting from the drilling. We get pretty well mineralisation from 0 to 120 metres. A lot of the mineralisation terminated in the mineralisation. As you can see, there's a kilometre wide zones of mineralisation. Typically, it goes about a third of a kilo. You can see from that it's about a third of a kilo of NdPr. But there's also dysprosium and yttrium in there, which when we did a preliminary leach test, we were able to get 80 to 90% of the NdPr and about 40 to 50% of the yttrium and dysprosium. The dysprosium, that number doesn't probably look that particularly high, but when you're typically mining these bulk mining propositions, mining about 10 to 15 million tonnes a year. So with that sort of dysprosium number, even at 50% recovery, you're probably enough to supply about 5% of the world's dysprosium right there. So the mineralogy, we did a little bit of mineralogy with ANSTO, preliminary stuff on some surface samples, the surface sample that we got. And again, it showed this bastnasite and synchronisite, which are these fluorocarbonate minerals. And these are reasonably soluble and easy to get into solution. And that's half the problem with a lot of rare earth projects. A lot of them are in silicate minerals or apatites or phosphate minerals, which are a little bit harder to dissolve. But the fluorocarbonate is reasonably soluble, and that's what encouraged us when we saw that this was a fluorocarbonate-hosted rare earth mineralisation. And the fact that it's hosted in a granite, it's low acid consuming, so we don't expect the reagent cost to be that high. So the little preliminary test that we did on these surface rock chip samples showing that we could get 80 to 90% of the rare earths out using a sort of moderate strength acid at 70 degrees in 6 hours. So it's a positive first test from just a completely walk up sort of situation. But it's, again, this metallurgical work is subject to a lot more work. But we're expecting it'll give us a similar result, and we can do some optimization work as well. So this is some of the leach tests that we did, the leach test that ANSTO did, and just showed we can get a lot of the rare earths out, 80 to 90%, and the dysprosium and yttrium was about 40 to 50%, and without doing too much to it. So that was a pretty of a positive early in the project. So we've since drilled, got these big wide zones, and so going forward, the key for this project really is that it's got this potential to be this large. Is the mining advantages that it's got this potential to be this vast open pit. It's 1,000 meters wide. It's got a very low strip ratio, so it's got some huge advantages there. There's potential for pretty low processing costs. So the bulk of the rare earths are in these these soluble fluorocarbonate minerals. So they're in favourable low acid consuming rocks, but they're also low in uranium and low in thorium, which again makes the whole processing side of the equation very, very simple. Infrastructure, that in the background there, you're seeing the smelter at Mount Isa. There's an acid plant there at Mount Isa. It produces acid, so only 20 k's from an acid plant. Potentially, there's a huge workforce, about 30,000 people that live in Mount Isa. We've got a gas pipeline that traverses the project as well. So there's all these great infrastructure advantages for this project as well. This style of deposit, there are examples of it elsewhere in the world, but they are a copper equivalents or uranium equivalents. But we've found what we think is a rare earth version of one of these type of deposits. So in these granite-hosted weak acid soluble deposit types, it's one of the larger deposits that in the world is for copper as chalcocite in a weathered porphyry in Morenci in the US, which is a company that I used to work for with Phelps Dodge and became Freeport. That's basically, they can mine extremely low grades there. I think they were mining 800,000 to a million tonnes a day on those sort of operations. Uranium, probably the thing that we can compare it to geologically, is the uranium as uranite in a granite-hosted soluble uranium mineral deposits in Namibia. This is the Rossing mine and the Husab mine. These typically mine sort of 300 to 600 ppm uranium oxide, and the cutoff grade on these things is about 100. So they're, again, easy to dissolve ore minerals hosted in a non-acid consuming granite, and that allows you to mine to these low grades. And we think we've got something similar, but in the rare earth space, because we've got these soluble ore minerals and we're hosted in a low acid consuming granite. So these bulk deposits, or this style of granite-hosted weak acid soil deposit type, these deposit types offer a really large metal inventory. So the deposit that we've got there is 10 to 14 kilometres long and 1 to 2 kilometres wide, and it's still open at depth. So they've got these large metal inventories. They've got a consistent metallurgy which has low complexity, and that's key to keeping the costs down. They've got unreactive granite host rock. They've got low reagent consumption. They have simple bulk tonnage open pit mining, which offer low stripping ratios. They've got low contaminants. They're low cost, and all this translates into being really low cost producers, which means at the end of the day that you can mine very low grades, and these projects often have very long lives. So typical Rossing, I think, has been going at least 30 to 50 years of extremely low grade mining of uranium oxides, and that typically that would be that. When the uranium price goes to about $6 or $8 a pound, probably the only deposit left operating in the world is the Rossing mine. So that's the kind of projects that we're sort of comparing this thing with what we've got here at Sybella, we think. So what next? We currently we've completed this red line here of drilling, shown here in the red. But what we're going to be doing next is a couple of things. We're going to be using those RC samples to try and optimise what sort of metallurgical data we can get out of those RC traverses. So we've got these chip samples coming out of this from the RC that we're going to do some lease tests and optimization tests to see which is the best type of acids and what type of sort of flow sheet design we can get out of it. We'll probably end up from that. We'll end up doing a little bit of make some bond work assumptions at this stage and do some mining studies on it just to see where and what this might look like from an economic point of view. Can we economically extract it, and what sort of size and what sort of cutoff grade does it fall over? So we'll play around with that in the next few months. We'd look to try and get some of that bench work stuff done on our RC samples between now and Christmas. And then if that's still all pretty positive, we'll do the heritage work at the moment and get ready for this step out drilling. And this step out drilling is on 1.6 kilometre spaced lines, 200 metre spaced holes, really to scope out what the size of this thing might be. And we're pretty confident we've got no shortage of tonnages. It's really about for us, really, but more about the confirming the metallurgical properties that we already suspect are here. And once we've got that, then we're off and running. So it's there's a lot of government grants available for this sort of stuff. The Queensland and federal governments have got a lot of critical metal type stuff going. So we'll look to see if we can access some of that and R&D grants for the metallurgy. So they shouldn't cost us too much money, I hope. So yeah, short and sweet, Jessica. I think that's most of it. Again, we only really put this out in the market a couple of weeks ago, and I haven't really got too much more to say on it other than what's in the public domain there. But that's most of it, I think.
That was awesome. Thank you. Everyone that's still an attendee, I'm going to promote you up as panelists. You're welcome to come through and you can chat with Rob directly. But I did see one in the chat. What's the regolith like? Okay,
so the regolith, I'll just go back to that section. So the regolith is a cover sequencer. So basically you've got a thin veneer of sand on the top 1 to 2 meters. And then after that, you're into weathered granite, but it's not heavily clay altered granite. It's just a little bit of partially weathered granite, I guess you'd call it sap rock, and then into fresh rock. So this is probably the sap rock here, this what we call broken granite. And then you've got your fresh granite, and then there's a thin veneer of sand on top, 1 to 2 meters generally.
Yeah. Where do you sell? Is there an open market?
So I mean, that is the problem with all sorts of rare earths, is that there is a limited market on all that sort of stuff. So that's I think that's the commodity that you're dealing with when you're dealing with rare earths. I think that market's growing though. Neodymium is again your battery is through your magnets that you used in electrical motors for wind turbines and electric cars, etc. So I think that's the end users are probably the car manufacturers. So ultimately, I assume they'd be the guys buying this, or the magnet producers. China certainly is one of the bigger producers of rare earths, but they're also one of the biggest purchasers of the stuff. So again, all that side of it yet to be seen. But I think America's trying to secure an alternative supply to China with the rare earth space, and I think that's why there's been a lot of investment from US governments and stuff into Australia looking for rare earths. So it's an emerging market, a bit like the lithium space.
Yeah. What's the soil geochem footprint?
What we found when we did a trial soil line across the top of the historic this historic work, what we found when we did some trial soil lines over that is that the soil lines weren't at the time reflecting what was below, because the sand veneer on top is transported. So we haven't done regular soil sampling over this thing, because we've found that the regolith wasn't honouring what we were seeing in the historic drilling. The soil samples were too diluted in the surface, and yeah, they just weren't offering a clear targeting thing. We'll try it. now that we've got some better drilling on what's going on here, we'll probably have another crack at that with some other techniques. But our initial work showed that the soil lines across the top weren't actually reflecting what we're seeing directly underneath it. So I haven't used it as a targeting tool.
Mm-hmm. Are these uranium and presumably thorium values a hindrance to processing?
No, they're not. They're very low by if you are very extremely low, and they're not in a soluble form, so they're not that thorium and probably uranium, I suspect, is tied up in a monazite or a zircon or somewhere else, so it's not liberating when we put a weak acid on it. So we're just attacking the fluorocarbonate with the weak acid attack that we put on it.
Yeah. What's the next steps for the project?
As I sort of discussed on this slide here, the next step is try and optimise what we can get some confirmation work on the leach tests that we've done previously. For this yellow dot here is where we had the surface sample, which was before we did the drilling, and we just want to get some confirmation work on that. So we're doing that at the moment. We're about to embark on that with the RC chips that we've got, using that. Ideally, you'd want to use core, but we've got the RC chips, so we'll try and optimise what value we can get out of those chips. So we're doing some different acid types, some different bleached, different temperatures, play around to see what's the optimum way to get this stuff out, and then we'll work out grind sizes and bond work index to see how hard it is and what sort of grinding we'll need. Once you've got those sort of things worked out, it's pretty easy then to throw it into a mining model with an open pit assumption about the size of this thing, and we'll put a mining model together internally. We probably won't be able to put it out to the market because of it's not based on an inferred or an indicated resource, but it's something we need to do internally before we jump into a big drill out program.
Yeah. Is this part of the Sybella granite unique, or should we all go out pegging anything called Sybella?
It's unique in the Sybella suite, yes, and you can kind of get a glimpse of that from this traverse here. You can see the thematically coloured by neodymium and praseodymium, and this one really does light up. We've gone across 1, 2, 3, 4 different phases of the Sybella here, and a lot of them are just low level background neodymium values. Again, the difference between background and what we consider to be ore here is probably a sort of a factor of 2, but it's enough to be the fact that it's at surface. It's all the infrastructure pluses, and the fact that it's in a soluble fluorocarbonate mineral mean that's the difference between being an ore body and not being an ore body, I suspect. So yeah, not all Sybella granite is as rich as this particular phase.
Yeah. Would it be right to consider this an A-type granite?
We haven't sat down and done all that sort of whole rock chemistry. I don't think it's an A-type. It's not it, but there's a lot of smarter people that have done a whole lot of geochemistry on the phases in the Sybella, and I couldn't tell you at the time what exactly the detailed chemistry is on the granite at this stage. But to say it's K-spar quartz biotype, coarse, very coarse, and it's actually deformed. It's actually an older phase of the Sybella. So if that's any clues to you.
Yeah. Do you see this as a different style to Valhalla skull?
The Valhalla, that's the uranium deposits. They are the uranium deposits hosted in the Eastern Creek volcanic basalt. So yeah, it's completely different. And this is rare earths, not uranium. I suspect there are rare earths in those Valhalla, uranium deposits, but yeah, completely different. Nothing like it.
Yeah. Does the granite have any unique geophysical signatures, magnetics, rads, etc.?
Yeah, it's low magnetic, and as are the plutons around it. So they're just low magnetic plutons, which you can easily see in the magnetics, and they radiometrically they're quite flat. As you can tell, the thorium and uranium contents are very low, so they'd probably be high potassium, but they're not low thorium, low uranium, low magnetic.
Yeah. Thank you for the interesting talk. Do you have any thoughts about the origin and processes responsible for the rare earth enrichment?
I haven't gone into too much thinking on that one. It's fine. It seems to be disseminated throughout the granite quite evenly. You can tell from all our assays that it is quite even in its distribution. So I'm thinking it's a primary magmatic origin. I don't think it's a later hydrothermal overprint of any sort. So I think it's a primary compositional. Now, why this one's more enriched than the others, I couldn't really say at this stage.
Yeah. Does the Sybella granite host have a potassium radiometric response?
Yes, it would. Yeah, it's a lot of case bar in it.
Another thought, I suspect there would be potential extra value in the mine waste if it is just granite, example for construction material, etc. Do you agree?
Yeah, it's going to be a very benign waste from it. You'd probably even make cement out of the stuff. Who knows? It's not going to it doesn't have any sulfides in it. It doesn't have any deleterious type elements. So actually, it'll be quite a useful, potentially a useful product at the end. Once you crush it up and get the rare earths out, there may be something of value still in there for sure.
But no, that was really interesting. I think you've certainly sparked some interest here. So thank you for sharing and talking to us about it. And
Thanks, Jessica.
good luck with the next steps. I can't wait to hear more.